last lecture we looked at stacks as a data type. We saw how to implement stacks using an array. Today we are going to look at queues and linked lists, and in the later part of the class today we are going to do sequences. So, in particular, so in the first part of the class today I am going to do queues, linked lists and double ended queues. So, what is a queue and how does it differ from a stack? So, if you recall, the stack followed the last in first out principle. The element that was inserted last into the stack was the one that was removed first. Right? A queue on the other hand follows the first in first out principle. Whoever joins the queue earlier is the first to be removed from the queue, is first to be processed. Right? So, you are all familiar with queues. So, the elements, so in a queue, for instance, here there is a notion of a front element and the notion of a rear element. Yeah? When an element is inserted into this queue, it comes here at the rear. When an element is removed from the queue, the element, or if I remove an element from the queue, it is the element which is sitting at the front here. So, this is the element which would get removed. Yeah? There is no notion of बीच में queue join करना, right, which you are all guilty of. So, we always insert an element at the end, and when we remove an element, it is always the element at the front. So, the queue is also an abstract data type, and we can define a few methods on the queue. These are the standard operations as you can think of. One would be to create a queue, right? The method new would create a queue. NQ is the method to add an element to the queue, and DQ is to remove an element from the queue. Yeah? When you DQ and if after you DQ a queue, when you remove an element from the queue, you get another queue. The front is a method which gives me the front element of the queue. Okay. How does it differ from DQ? It does not remove the front element, it only tells me which is the element at the front of the queue. Besides that, we also have some other support methods to implement a queue, and one could be size, and one is empty. Size would tell us how many elements are there in the queue, and is empty would tell us whether the queue is empty or not. So, it would return a true if the queue is empty and false otherwise. And just as we had defined some axioms for the case of stacks, we can define similar axioms now for queues. Right? So, if I have if I create a new queue and I insert an element or an NQ, an element V, and then I say what is the element at the front of the queue, then it should be V. Yeah? You understand why this is true. Suppose I create a new queue and NQ an element and I DQ an element, there is an extra queue here, I DQ an element, then what should I get? I should get the empty queue, right, which is the same as what I would have obtained if I had just called new. Similarly, here if I had a queue, capital Q, and I enqueued an element W, which means I added this element to the queue, then I added another element V to the queue, right. So, which is coming before and which is coming later. So, W is ahead of V in the queue. Now, if I call front, then what should I get?
W.
So, first you have W, all the elements of, first you have all the elements of Q, followed by W, followed by V. So, which is the element of the front at the front of the queue? Whichever is the element in the front of Q comma W. Why have I written front of Q comma W and not front of Q? If Q is empty. Yeah, because if Q is empty, then this would not, if I had just written front of Q here, that would not have been defined, right. If a Q is empty, then there is no notion of a front of the queue. So, that is why I have written Q comma W, front of NQ comma W. Okay. So, same thing as before, I had a QQ, I first inserted W into the queue, then I inserted V, and then I removed an element, right. So, which is the element which gets removed? Whichever was the element at the front of Q. and if there was q was empty, then it would have been w, right. So, then this operation is the same as saying that I had q, I removed w, I added w to the q, then I removed an element from the q, right, and then I added v again. Right. So, the q that I would obtain and as a result of these two procedures should be the same. Yes or no? Right. Let us just check it out. Let us assume that q was initially empty. Then what does this give me? First I added w, then I added v, and then I removed an element. If I removed an element from the q, what would I get? W. W is removed, right. So, what should I get the remaining q as? V. Let us look at this now. Q is empty, I added w to the q, then I removed an element. So, once again I am left with an empty q, and then I enqueued v. So, I have a q with v in it. So, if q is empty, then it is in both cases the q will have only v in it at the end of the procedure. If q is not empty, then when I enqueued w, then I enqueued v again. So, I have a q in which I have first all the elements of q followed by w followed by v, and then when I dequeued, what should I be left with? I will be left with the q without the front element, the original q without the front element followed by w followed by v. And let us see if we get the same thing here. I started with q, I added w to it. So, now I have a q in which I have q and w, then I dequeued, which means I removed the front element of q. So, I have the q now contains all the elements of q except the front, then I have w in that q, and now I added v at the end. So, I get the same thing. How do we implement a queue? We are going to use an array to implement a queue, and we are going to use it in a circular fashion. What does that mean? Right? Suppose someone tells us that this queue is never going to be larger than n elements. So, I am going to allocate an array of size n. I am going to have two variables f and r, f for front and r for rear. F is the index of the front element of the queue, right. So, wherever is the front element is in the queue, f will be referring to that position, and r is an index which is the element following the rear element. So, as you can see, r refers to this location. This blue part is the part which is occupied by the queue, right. How did the key q reach this place, right? I would have started with the front here, right. The first element I inserted must have come here, then the next element I inserted must have come here, the third element I inserted must have come here, and so on and on. But then I am also deleting elements. When I am deleting element, this element goes away. So, in effect, the elements of the queue kind of drift right, yeah, and so we are now at a stage where the front element is here and the rear element is here. This implies essentially that we have kind of deleted f minus 1 elements, let us say, since the queue began, right. Not accurate, completely accurate the statement of mine, but you will see what I mean by it. Okay. Now, I have said something like in a circular fashion. What does this mean, and why am I saying such a thing? Yeah. So, let us say we kept inserting elements in this queue. I inserted another element, I inserted another element, I inserted another element, and now I cannot insert any more elements, right, because I have already reached the end of this array. But I have space available here in the front. So, what will I start doing? I will wrap around, I will start inserting the elements here, right, and this is what will happen, right. Your queue can at some point also look like this, where this is now the front. You recall in the previous slide, front was to the left of the rear, but now front is to the right of rear, because your queue is now starting from here and going like this. Now, when I insert an element, it will come at this location, next element will come at this location, and so on. Yeah, everyone with me? Okay. Now, initially our queue began. So, when we started, front was referring to this location, or where was front referring to? when we begin, where should front have referred to and rear have referred to? F should have been at -1, right? Because we said front refers to the first element of the queue. There is nothing in the queue, then F should be -1. And rear refers to 0, right? Because rear refers to an empty location always. Okay. So, what does, if at some point I reach a situation when F equals R, what does this mean? Empty or full? Full or empty? When it becomes empty, what will happen? So, suppose now at this point, starting from this point, I kept removing the elements. I didn't add any other element. मैंने इस element को delete किया, then I deleted, I removed an element, I removed an element, I removed an element, I removed this, I removed this, I removed this, then I removed this, right? Now where would F be? F would be incremented to R. So F becomes R. When F is R, the queue is empty. Right? But suppose I kept incrementing, I kept adding elements to the queue. So when I add, R will move one step, R will move another step, and so on. When I add an element here, then R would be pointing, would be referring to here. So again F equals R. Right?
Not add the nth element.
We will not add the nth element.
Add only n minus 1.
Right. So that's what we are going to do. So there is an ambiguity here, right? So we have to resolve this in some manner. F equals R can mean both empty or full. And since we will have a problem if we don't know whether the queue is empty or full, we will try and ensure that we never add n elements to the queue. When the queue has only n minus 1 elements, तभी हम उसको full declare कर देंगे. We will declare it to be full. Okay? So that's what we are going to do. Okay, let's look at the code for NQ. So this is just pseudo code. If the size of the queue, if the number of elements in the queue is n minus 1, then we are going to stop. We are going to say, sorry, the queue is full. We return the queue full exception. Otherwise, if such is not the case, then at the rear location, put the element that you are trying to insert, yes, and increment R. And why is this mod n required? Because we need to do the wraparound.
It's circular.
Yeah, it's circular. So wraparound, right? So when R becomes, so R or the indices go from 0 through n minus 1 only. So when I increment R, if R is already n minus 1 and I increment R at this point, then I don't want it to become n, I want it to become 0. So n mod n is 0 and I'll have it set to 0.
Sir, size is a method or a variable?
Size is a method, so this should have been size bracket. Yes, thank you. The size is a method. Okay, now what does the method size do? It returns this value. Why this value? Why should I not have written just R minus F?
When it is circular, then R is.
So R minus F is negative in this setting. But in this setting, R minus F tells me exactly the number of elements in the queue. Right? So R minus F is the correct thing, except that it might be negative. Right? So how many elements are here now in this queue?
N minus R.
N minus R plus F. Right? So sorry, it should be N minus F plus R, whatever, one of these things, right? So this would be the number of elements that you would get. This quantity would always be positive, because R minus F can at worst be minus n, right? So n plus R minus F would always be a positive quantity. So you can return this as the size. This will tell you the right number of elements, right? So check this out if you are confused. Is empty. This is a method, and we said the queue is empty if F equals R, right? There was this ambiguity, recall? So we said, but we will never add more than n minus 1 elements into the queue. So if F equals R, that means the queue is empty and not that it is full. So if F equals R, we will return empty. We will return true for this method. For front, if the queue is not, if the queue is empty, then raise an exception, otherwise just return the front element, right. We are not removing the front element, that is done here. In this case, we will increment the front index and remove the front element by setting this to null. Yeah, is this clear to everyone? Any questions? You can also implement a queue using a linked list, right. So, we saw a array to implement our queue. The disadvantage of using an array is fixed size, right. So, if your queue, if you knew what the maximum size your queue can take, then it is okay, but if you had no idea what the maximum size could be, you could either use the method that we did in the last class, wherein when the size increases beyond what we have allotted, then we double the size of the queue. You could either do that, or you could use an implementation which uses a linked list. And I assume all of you are familiar with linked lists from your previous course. So, what is essentially a linked list? It has nodes and it has pointers which are basically referring to the next nodes in the list. This is also referred to as the head of the list, and this is referred to as the tail of the list, and each of the node has some element, some data in it, right. Now, if I am going to use a queue to, if I am going to use a linked list to implement a queue, then question is whether this should be the front of my queue or this should be the front of my queue. Yeah, which should be the front of my queue? The head of the list has to be the front of the queue, right. The tail of this list cannot be the front of the queue. Can someone tell me why the tail of the list cannot be the front of the queue? Why can't I have my queue in which the first element is this, the second element is this, and the third element is this?
Adding elements will be adding at that side. So we are adding at the loose end. We'll add at the loose end.
Remove. Exactly. So, the problem is with removing. Note that I cannot remove this element. The linked list does not permit me to do this. Can I remove this element from the linked list? Not directly. Why not? Because to remove this element, I have to change this pointer, but I have no way of accessing this pointer. Yeah. So, I cannot remove this element. I can remove this element, no problem, but I cannot remove this. And in a queue, the removal is being done at the front. Yes, we remove the element at the front of the queue. So, since I cannot remove the element which is sitting here, I cannot call this the front of the queue. So, I would like to have this as the front of my queue. Okay. So, let us see how we are going to implement our methods. So, suppose I have to dequeue, which means, so this is now the front of the queue is to your left, right. This is the front of the queue and this is going to be the rear of the queue. So, if I have to remove the element at the front of the queue, I have to dequeue, then what should I do? The head should now point to here. Yeah, that way this front element will get removed. So, I just increment, so I just make the head point to this element now. Yeah. So, in this manner I can delete at the head very easily, I can delete this element very easily. I can also insert a new element at the head very easily, right. I just create a new node and I connect it here and I make the head point to the new node. So, inserting at the head is also very easy, right. Everyone follows this dequeue operation, right. So, this is the front of the queue and I can just kind of move the head one step to the right and in that manner remove the front element of the queue.
You have to put null in the node of the first.
Yeah, that will also need to be done. Okay. Now, if I have to add an element, enqueue an element, now recall enqueue has to be done at the rear of the queue. So, this is my queue, this is the rear of the queue, I need to add a new element here. So, if I need to add an element, this pointer should now get modified to point to this element and tail should be updated to point to this element now, because this will become the new tail. And well, this pointer should be null. right. So, I can always add an element at the tail, and the question that we discussed just now, it is difficult to remove an element from the tail. You cannot do it in constant time, right, because if I want to remove this node, how do I remove this node? Because to remove this node, I need to access the previous node. So, the only way you can do it in this kind of a list is to start from the beginning and go move all the way to the right till you get to this, and then you will be able to access the previous node.
So why can't we just declare the last tail to as 5? But what's the problem actually in removing the tail?
What is the problem? So, his question is, what is the problem in removing this node from here? What is the problem in removing this node? The problem in removing this node is that after I remove this node, what is the new tail of this list? It is this node. I have to make this point to here. How do I get to this node? How do I get to this node? I need to go through the entire list to get to this node. That is very expensive. I am not saying it is not possible to do it, it is just that it is a very expensive operation, right. So, it is not worthwhile to remove at the tail, and so we will remove at the head and add at the tail, which means that the front of our queue will be at the head and the rear of the queue would be at the tail. Okay. So, that is as far as the queue data type is concerned. Now, I am going to introduce another data type which is called a double ended queue. Right. What is a double ended queue? It is a queue in which we support insert and delete operations at both ends. Right. You can, so we will now have insert first, insert last, remove first, remove last. Insert at the front of the queue, insert at the end of the queue, remove at the front of the queue, or remove an element at the end of the queue. Of course, we have the element operations first and last also. Right. So, such a thing is called a double ended queue. Right. At both ends, we can do both the operations of insert and delete. And as you can see, a singly linked list is not a good idea to implement such a double ended queue. Why? Because as I have said repeatedly, we cannot remove the element at the tail, or it is expensive to do this. So, what is a good solution to this problem? So, we are going to use what are called doubly linked list to implement double ended queues. So, first, what is a doubly linked list? A doubly linked list has nodes with 2 pointers, one a next pointer and one a previous pointer. Right. We are also going to have 2 sentinel nodes here, and I will come to the need for them in a minute. Right. So, but each node has 2 pointers, one pointing to the next and one pointing to the previous. Now, using such a list, we can implement all the operations of a double ended queue in constant time. Why? So, now the problem earlier, if you recall, was how do I delete this node which is at the end? How do I delete this now? If I have, so I have a pointer to, so trail these, and these are 2 sentinel nodes, and I have pointers to these 2 nodes. How do I get to this element? I just follow the pointer once and I get to this element. How do I delete this now? Move to the previous port and set its next pointer to trailer, and send the previous pointer of trailer to this node directly. We will perhaps see a slide on this one. Okay. So, we will need header and trailer nodes in a doubly linked list. Header, so these nodes are called sentinel nodes or dummy nodes because they do not contain any data inside them. Right. They are just there to mark the start and the end. Okay. This is useful.
This part is not clear. How you basically delete the node?
How do you delete the?
How you delete from that side?
Okay, we come to that in a second. Okay. So, that is answering his question, how do you delete at the end, right. So, here is those who have not followed it. So, I have to delete San Francisco, right, out of this list. All I have to do is make this pointer point to here, make this pointer point to here, right, and then this node is out. This becomes my new list. Okay? So, that was the only thing we could not do in a singly linked list, right. So, I have shown you how to do it here, and so all the other operations you can understand can also be done in constant time therefore. Any questions? Right. So, using a doubly linked list, we can implement all the operations in constant time, all the operations of a double ended queue in constant time. You can insert at the front, insert at the end, delete at the front or delete at the end, all in constant time. Right. What does constant time mean? Time which is independent of the number of elements in the list. Right. आपकी list कितनी भी बड़ी हो, your turning time will not be dependent upon that. Okay. Now, a double ended queue is a fairly generic data type. It can be used to implement other data types also, right. So, suppose you had an implementation of a double ended queue, you can use that to make a stack or make a queue, and we see how, right. So, I have a implementation of a double ended queue, sorry, I have an implementation of a double ended queue. I can use the methods of this implementation to implement a stack, right. So, for instance, the method top would correspond to, let us say we keep the top of the stack, we make the top of the stack correspond to the last element of our double ended queue. So, the method top would correspond to return, give me the last element of my double ended queue. The method push would now correspond to inserting at the end of my double ended queue, and the method pop would correspond to deleting at the end of my double ended queue. Right? There is nothing sacrosanct about last here. I could also make this correspond to the front element of my double ended queue, in which case this would have been front, this would have been insert front, and this would have been remove front. Yeah, you could use it either way you like. And size just corresponds to size of my double ended queue, and is empty just corresponds to is empty of my double ended queue, because these are only dependent upon the number of elements in the queue. Right. Similarly, I can use a double ended queue to implement a queue. Right. So, now front would correspond to the first element of, to give me the first element of the double ended queue. NQ, what do I do in NQ? I insert at the rear. So, that corresponds to insert last. And when I say DQ, I say remove from the front. So, remove the first element of my double ended queue. Right. So, if I have implemented, if I have a DQ implementation, I can use the methods to implement a stack or a queue or one of these data types. Any questions? Right. So, this is the notion of an adapter. So, what we have used a double ended queue to implement a stack or a queue, and this is an example of an adapter pattern. So, adapter patterns implement a class using methods of another class. So, in general, adapter classes would specialize general classes, and we can have applications of this. One application would be we can implement, as we just saw, we can implement by changing some methods. We can implement, for instance, a stack using a double ended queue. Another application would be, for instance, in the last class we saw an implementation of a stack, right, using an array. Stack, we defined an interface called stack and we implemented it using an array, right. That implementation had called it an array stack, and what elements, what are the contents of this array stack? They are any arbitrary objects, and I can adapt this implementation to an implementation called integer array stack, which only has integer objects in it. So, all I would have to do is change the or suitably cast the type of the objects that I am pushing into this stack or removing out of this stack. Yeah. There is another data structure called circular list, and it is very simple. In this, the last element is pointing to the first element of the queue of the list, right. So, there is only one pointer which is pointing to, so there are no two pointers, first and head and tail, there is only one which points to the start of this circular list, and you can use this data structure to implement both queues and stacks also, right. How will you use this to implement a queue? In a queue, once again, this is the what is this? This is the front of the queue or the rear of the queue? We will make this the front of the queue, and the rear of the queue is this, right. So, when I have to insert an element into this queue, when I have to add an element, what should I do? How will I add an element at the rear? Right. I will add an element, let us say here, pardon? I will add an element here. What should I do?
This pointer
will make its pointer point to this guy and make the head point to
and make that element point to the
yeah, it is not straightforward, right, because if you were to do that, how do you make this point to the new node that you have just created? That has to be done. Okay, after all, what we want is that we want to create a new node here. Right. So, this will become the new node that the element that you are inserting will now go into this node, make it go into this node and create a new node and copy this element into that new node, right, and make the head point to that new node.
So, even copying can be very costly.
Copying is not costly because here you are only copying the reference. Yeah. So, think about this, it is very straightforward. So, in this manner you can insert an element at the you can insert an element in this queue if you are using this to implement a queue. To remove an element, removing an element corresponds to removing the first one, right. How do you remove the first one now? Right. If I were to just remove this element here, then how do I make this point to this? Problem? Right. So, what do you do again? Let us remove this one, let us remove this node and copy the contents of this node to here. Yes, we have to remove Rome. How do I remove Rome? I copy Seattle to Rome. So, this now has Seattle in it and I remove this node. Copy here means just changing this reference. Yeah, अभी ये यहाँ point कर रहा है, अभी इसको आप यहाँ point करा दीजिए. Okay. So, that's all I wanted to discuss about queues and double-ended queues. So, now we are going to go to the second part, and we will quickly look at some sequences. So, vectors, we are going to be talking about vectors, we are going to be talking about positions, we are going to talk about lists and general sequences, right. So, they we will be using the data structures that we have seen so far, arrays and linked lists, to be able to implement these data types. So, what is the vector data type? The vector data type is a sequence of n elements that supports these methods. So, these are indicative methods, these are not all the methods. So, essentially in a vector, so it is a sequence where there is a notion of rank with every element of the sequence, right. So, think of a sequence of elements, right, 7, 11, 13, 19, and we know that 7 was the first element, 11 was the second element, 13 was the third element, and maybe I said 5. So, 5 was the fourth element. So, with each element there is a notion of a rank, right, and then I can have methods like give me the element at rank r. So, rank here corresponds to, let us say, rank are integers, right. So, the first element was element at rank 1, the second element was element at rank 2, and so on. So, suppose I ask you give me the element at rank r, or replace the element at rank r by the element e. Insert an element at the rank r, insert the element e at rank r, or delete the element at rank r. Right? I could have such methods. Yeah. Note that when I remove the element at rank r,
so when we are saying that delete the element at rank r, so the next element will still have that same rank.
right. So, what happens? So, think of rank as, for instance, let us say the rank of the students in a particular class, right. There is a departmental rank 1 and a departmental rank 2 and a departmental rank 3 and so on. Now, suppose departmental rank 4 does a department change and goes to some other department. Now, who has department rank 4 now? Whoever had rank 5th earlier, right. So, the same notion. So, everyone would move up by 1 rank. Yeah. So, let us see how to implement this data type. What do you think is a natural data structure? What would be one data structure to implement this data type? You can implement it using arrays. Let us see an implementation using arrays. Yeah. So, what am I going to have? I am going to have this array in which I will have the element with rank 1, the element with rank 2, the element with rank 3, and so on and on. Yeah. And now, if I have to insert an element at rank r, so I think, yeah, so no, this is going as element at rank 0, and let us say my ranks are beginning from 0, rank 0, rank 1. So, if I have to insert an element at rank r, what is the thing I have to do? I have to put an element here, which means that I have to shift all these elements one step to the right. So, that is what I am doing here, and then I put an element here, right. So, what are we doing? We are in a for loop, we are moving first n minus 1, we are moving one step to the right by this statement, and we are doing this first n minus 1 is moved one step to the right, then n minus 2 is moved one step to the right, and so on and all till r is moved one step to the right, and then finally, the element e is put at position r, and the size of the thing is increased by 1, right. N suppose stores the size of the vector. Similarly, when I am removing an element at rank r, I am essentially shifting all the elements one step to the left, right. All elements starting from this should be r to n minus 2 is okay. So, S I gets S I plus 1, the element at location r, the position the here I will get the element which was sitting at location r plus 1 and so on. Okay. How expensive are these operations in the worst case? Order n. In the worst case, because we might have to shift up to n elements to the right or to the left, right. So, this implementation is expensive from this point of view. If I have to do these two operations, insert at a certain rank or remove at a certain rank, I have to, in the worst case, spend order n time. The other operations are faster though. Element at rank r, how much time does it take? Because I just go to the rth location in that array and retrieve the element sitting there. Replace at rank r comma e, again order 1, because I just go to the rth location and replace that element with the element e. Right. So, this is a chart which shows the wide time complexity of the various methods. All methods except insert at rank and remove at rank take constant time. These two methods could take order n time in the worst case. Can you think of some other way of implementing this thing? A doubly linked list, right? Doubly linked, you can use a doubly linked list to implement a vector. So, I am showing you here the operation of inserting at a certain rank. Now, what is the rank? This is the header. So, this is the element which is at rank 1, this is the element at rank 2, this is the element at rank 3. Sorry, this is the element at rank 3. So, now suppose I want to insert an element at rank 2, what am I going to do? I have to make a new node and I put it between 1 and 3. How much time does it take? Huh? How much time does it take?
At maximum order n minus 1.
Okay, so everyone understands the process of insertion, right? I create this node, and how do I insert? I make its next pointer point to this node, I make its previous pointer point to this node, and of course, iska next pointer would point to this node and iska previous pointer would point to this node. So, this is how I insert New York, and this is what I get after insertion. Now, there are two issues. First, if I know where I have to insert, then I take constant time, but to find out where I have insert, I might take order n time. Yes, because if I say insert at rank 17, I have to step through that linked list, go 17 positions, and then I would know I have to insert at this location, right? But once I know I have to insert at this location, then it's easy. Then it's 3 or 4 pointer changes which I have to do to insert the element at there. Okay. So, this would be a Java code for inserting at a rank. Now, here I am assuming the existence of this procedure, node at rank, right. This is a method that I am going to be defining shortly. What does this method do? Given a rank, it tells me which is the node at that rank. Yeah. So, for instance, here I had to insert this node at rank 2. First, I will call this procedure with rank 2. So, it will give me this node, because earlier it will give me this node, because this is the node at rank 2. Now, what do I have to do? I have to get to the previous node of this node. I get this node at rank 2, I get to the previous node of this node. So, this is the node at rank previous to rank 2, which is at rank 1, and the new node that I have to insert has to be between this and this, right. So, this is I create the new node and I set its previous field to refer to the previous node, and I set its next field to refer to the next node. This was the node at rank 1 and this was the node earlier at rank 2, right. So, in this manner I create a new node at the appropriate place, and then I also need to set the previous and the next field of this node and this node, and that is what I am doing here, right. So, it is not doing, do not get intimidated by this code, it is just doing what is shown here in the picture, and that is all, right. All I am doing is assuming the existence of this procedure, which given rank will tell me which is the node at that rank in the original list. Yeah, please do not try to copy this either, these slides will be available on the web. Okay. Now, here I show you the process of deletion. So, if I have to remove the element at a certain rank, how do I do that? So, suppose I have to remove the element at rank 3. So, once again I will first find out the node which is at this rank. So, I get to this node, and then all I have to do is go to the next node, go to the previous node and update their next and previous pointers. Yeah. So, this will now point to this and this will now refer to this. In this manner I will get rid of this node, and this is the list I will have at the end. And similarly, I can write down the Java code for doing this. Once again, I am assuming the procedure node at rank, which given a rank tells me which is the node sitting at that rank. Okay. Now, how do I implement this procedure node at rank? Well, there is nothing else I can do except to march through that array, march through the list and find out and keep incrementing my counter until I reach that rank. So, I have done essentially that, except small improvement, that if the rank is less than the number of the size of the list by 2, then I start from the header, and if it is more than size by 2, I start from the tail, just to small improvement and nothing more, right, but you could do such a thing. Yeah, because if you are looking, if your list had 100 elements in it and you are looking for the element at rank 98, then there is no point to starting from the header. It is better to start from the tail, right. So, that is as far as the vector abstract data type is concerned, except that when I say rank, when I say remove the element at a particular rank or insert the element at a particular rank, as we have seen in both the implementations, we have a problem, right. Whether we use an array or a list to do that implementation, we seem to require order n time in the worst case, just to be able to, in the list, just to be able to find out where that element is, where the element corresponding to that rank is. And in an array, while we know where the element corresponding to that rank is, we have to move the elements when we insert or delete, right. So, linked lists are better in supporting node based operations, right. I have a linked list, I tell you this node, delete this node, then you can, if it is a doubly linked list, you can delete that node in constant time, right. Or if I say insert a node here and I say, this is a node, insert a new node after this node, I can insert a new node after that node in constant time. Or if I say delete the insert a node before this node, again I can insert a node in constant time, right. So, we have this data structure which is very efficient, which can do constant time operations, provided we give it access to the node. We somehow access the particular node at which we want to do the insert or the delete, right. So, that is why, so that is what is mentioned here. You can remove at a node, or you can insert after a node, or you can insert before a node, all in constant time, right. However, when I give you access to a particular node, then in some sense what I am doing is I am also telling you how I have implemented my list, right, whether it is a doubly linked list or a singly linked list, and what are the what are the pointers and stuff like that. Suppose I want to hide all this information, so that you can still use node based operations, right, without knowing the actual implementation of how the thing was done, right, so that one can have many different implementations. So, we are going to do this using a notion of positions. So, positions is an abstract data type which intuitively captures the place where a certain element is stored, right. In your data structure, it captures किस place पर आपका element है, and there is only one method which is associated with this position, and that is the method element. So, given an object of this data type position, I can only call this method element on that object, and that will return to me, that will tell to me what is the element sitting at that particular position, right. If this is not making much sense, think of position as a reference to a particular node. Yeah, think of it as a reference to a particular node. You are familiar with pointers, so think of it as a pointer, which tells you, right, and but all you can do using that pointer is access the element that is situated in this node and nothing else. You cannot use that pointer to update the next or the previous fields, or you do not even know how this node is implemented, right, whether the implementer has used a doubly linked list or a singly linked list or a circular list, you do not need to know any of that, right. It is an abstract data type which hides all of these details, yeah, and you can only use the method element on the abstract data type position. Okay. And with the notion of positions, we will have so there will be a relative order on all the positions, just as it is in the case of a linked list, right. So, there is the first element in your linked list, the second element, and the position is referring to the first element or the second, or the first node or the second node or the third node of the list, right. Similarly, the first position, the second position, the third position, and so on and on. So, given a position, there is the notion of a position before, which refers to the node before that position, and a position after that position, right. And we can now define a list abstract data type which uses these positions, right. So, what would this abstract data type have? It would have generic methods like size and is empty. It would have query methods. So, given a particular position, I can have a method which asks is first, is this the first position of my list? If it is, this will say a yes, and otherwise it will say a no, and whether it is the last position of the list. I can have accessor methods which say first, last, before and after. First will give me the first position, last will give me the last position, before P will give me the position before this position P, and after will give me the position after this position P. I can have update methods like swap elements P comma Q. What does this do? Given two positions P and Q, it swaps the contents of these positions. Whatever are the elements sitting at these two positions, it swaps them. I can replace the element P, replace the element at position P with E, and similarly I can insert the element E at the very first position. Yeah, I can insert the element E at the last position, and so on and on. Yeah, and using a doubly linked list, you can actually implement all of these methods in constant time. Right. So, the list abstract data type is just, is your same as your linked list data structure, except that we are getting a abstract data type implementation of it. We are trying to capture all of those methods that you can do on a linked list as an abstract data type. Now, this data type can be implemented using a doubly linked list. It can be implemented using a singly linked list, except that it is perhaps more efficient if you implement it using a doubly linked list, right. In the using doubly linked list, all of the methods can be done in constant time. Using a singly linked list, some of these methods might take linear time in the worst case. Right. And finally, we have the notion of a sequence abstract data type. So, we have talked of the vector abstract data type, where there is a notion of rank associated with each element. Then there is the list data type, where there is the notion of positions, and the sequence abstract data type has both of these. So, it combines the vector and the list abstract data type. It inherits both of these interfaces, right. So, it is multiple inheritance. And besides the methods that I listed for vector and list abstract data type, it has two additional methods which kind of helps you go from one to the other, right. So, given a particular rank R, it will tell me, so the method at rank will return me the position corresponding to this rank, and given a position P, the rank of method will tell me the rank corresponding to this position. Right. So, you could have an implementation of this kind for a sequence. What is this? This is an array. Okay. Each element of this array refers to, so this is a position, and this is the same as this, right. So, this will, given this particular location, I can identify what rank it corresponds to by looking at this element. Yeah. So, now how is this method implemented? Rank of P. P corresponds to a position. A position here is one of these things, right. So, given a particular position, how do I know the rank corresponding to that position? I just look into this element here, that gives me the rank corresponding to this position. Given a particular rank, how do I determine the position corresponding to that? Suppose you gave me rank 1, I follow this reference, and this is the position corresponding to this rank. At this position, there is an element stored. What is the element? In this case, it is New York. At this position, besides the element, there is something else stored, which kind of provides a cross reference, which tells me what is the rank corresponding to this element in my sequence. Right. So, at each of these positions, I have an element stored and a rank of that element in my sequence. Okay. Now, suppose I had to insert an element at a certain rank, what would I do? Suppose I had to insert an element at rank 2. Yeah, can someone tell me what I will have to do? So, if I have to insert an element at rank 2, I am going to create a new position. The element would sit in that position, and this would now refer to that position. And of course, all of these will have to be moved one step to the right, and not just would they have to be moved one step to the right, what else will have to change? The ranks will have to change, because if this is moved one step to the right, then I have to go and update this entry to 3 now, right. So, again inserting at a particular rank will take order n time in the worst case. Similarly, deleting an element at a rank, right. Now, if I had given a particular position, if I wanted to delete the element at that position, what would I do? How did we delete delete an element at a certain position in the case of a doubly linked list? Okay, so you need to think about this. I'll leave this as an exercise to you. So, this is a comparison of the sequence operations. You can implement a sequence using an array in the picture I shown you previously, and you can also implement a sequence using a doubly linked list, and this would be the set of this would be the in the worst case running times of that. So, as you can see, in the case of an array implementation, if you want to insert an element at a certain rank, or you want to remove an element at a certain rank, it will take order n time. Now, if you want to insert after or insert before a certain position, yeah, this will also take order n time, and if you need to remove an element at a certain position, this will also take order n time. Right? Not so in the case of a doubly linked implementation, because then you can just zap out the element from there. Yeah, you can just update the pointers before and after and do these in constant time. But then what becomes more expensive here? Because in a doubly linked list, you cannot figure out the rank of an element. You have to go through the entire list to get to the rank, to figure out the rank. So, any rank based operation will now take order n time. So, whether you want to find the rank of an element, or you want to figure out the find out the element at a particular rank, find out the position corresponding to a certain rank, all of these would now take order n time. Okay. So, with that we will stop our class today. So, what we learnt today were queues, we learnt about double ended queues, we learnt about how to use linked lists and doubly linked lists to implement these data types. Then we also looked at the vector abstract data type, the list abstract data type, which is essentially a concretization of the linked list data structure, and we also looked at the sequence data type. A sequence data type is basically inheriting all the methods of your list data type and your vector data type. Yeah, okay.